In previous videos, we have investigated time series which has a stochastic trend, and the simplest time series with a stochastic trend is the random walk, which is characterized by the intercept and its own lag, and the coefficient in front of this lag is per definition equal to 1. And of course you have the error term. So this equation, or this process, is the random walk, and this process is the simplest process, which is non-stationary with a stochastic trend, because the variance of this process is non-stationary. It's increasing in time. And what if you have this non-stationary time series? You could work with it by differencing, right? You take the difference of the time series and then you can work with it, because then it's stationary. But what if you have a relationship here where you have an intercept plus the slope on a different variable? So this is a distributed lag model, and the model up here is an autoregressive model. So what if both these variables they have stochastic trends? What you could do, if they do not share the same stochastic trend, you could just take the difference of these two variables, and you can work with these stationary time series. But what if both y and x, they have a common stochastic trend? And this would then look like something like this. If this is, let's see, this is time, and this is y and x, and you have like this y of t, and you could have like the x of t down here, x of t, and you see that if one variable increases, the other one tends to increase. If one variable decreases, the other one tends to decrease, and so on. So visually, we could guess that these two variables, they share a common stochastic trend, and if they do, they are said to be co-integrated. And in this case, we can use this regression framework to investigate the relationship between y and x, but we need some new methods. A more formal way of expressing this is just assuming that the time series xt and the time series yt, they are I1, which means that they have a stochastic trend. And then you can assume that there is a number, theta, such that the linear combination of yt minus this number times x is stationary. It's integrated of order 0. And if this is the case, that that the linear combination here is stationary, then then x and y are said to be co-integrated. So if we go back to our tiny example, then we see that, well, maybe if we scale x by 3, then we get something really close to the y variable. So in this case, theta equals 3, then we get yt minus 3xt is stationary. So the 3xt, or 3 times xt, would be placed basically on top of the yt variable here, such that this difference between them would hover around 0, and hopefully with a stable variance. And a different way to say this is that if they have, if x and y are co-integrated, then they share a common stochastic trend, which is just something which affects both these variables, and we would expect it to, this stochastic trend, to affect both these variables in the future. And as such, we can eliminate the trend by taking the difference of the series. And always we learn better by example. So here we have the 10-year interest rate for a government loan in the US, and we have the 3-month interest rate for a government loan in the US. So this is the short interest rate, or the interest rate on a short maturity loan versus the interest rate on a long maturity loan. And the green line here is really the difference between these two interest rates. And this is just the 10-year interest rate minus the 3-month interest rate. So this is the term spread. And if we just look at the plot, then we can believe that the long-term and the short-term interest rates, they are co-integrated, because it seems like they share the same behavior, which is upward sloping in the 60s and 70s, and downward sloping from about 1980 and onwards. And you can see that this difference between this long-term and the short-term interest rate, for example, for this point in about 1997, then you have a large 10-year interest rate and a smaller 3-month interest rate, and the term spread is then the difference. Okay, but you see that the difference, it hovers around a small positive number, and it does not exhibit any trend on its own. And the volatility of this process is fairly stable as well. This leads us to believe that the term spread is stationary. So the term spread seems to be stationary. And I have to say, one of the theories in fixed income markets is the expectations theory. And the expectations theory says that the 10-year bond interest rate should be equal to the expected 3-month interest rates on treasury bills just rolled over. So you should get the same interest rate from lending money over a 10-year period as you would over 40 consecutive 3-month periods. So in theory, the coefficient, the number on the x variable should, or the scaling of the x variable should be equal to 1. So in this case, we could have the 10-year minus the 3-month interest rate, and we do not have to scale the 3-month interest rate. And this difference should be I0. It should be stationary.